All right, here's a transformer. I'm sorry, if Transformers fans. This is a lot more boring than the movie. Okay, but a transformer is a way if you have alternating current. Okay, it must be alternating current. Okay, because alternating current is constantly changing the flux, and if you have a changing flux, you can induce a current in the secondary. If it's a constant thing, then basically when you turn the current on, you get a little burst of current in the secondary. When you turn it off, you get a burst of current the other way, just like the demo that I did on the first day of induction. Okay, but if it's constantly changing, then you have the primary sets up a magnetic field in this wire, that first goes this way, then it goes that way, right? And that magnetic field is carried around. These things tend to be like conductors of magnetic field, right? And so ultimately, this primary thing changes the magnetic field in the secondary and induces a current in the secondary, okay? Transformers are primarily used to step voltages up and down, and why that is, we'll learn, but stepping it up to a high voltage reduces the current, and then you lose less energy, because the energy is lost by I squared R, right? So if you can bring the current down, the power loss by these transmission lines is much, much less, okay? The other thing, by the way, that transformers do is they isolate systems, right? So you can have a isolation transformer that allows you to power something that has to operate, say, at a really, really high voltage. Like when I was in McAllister, they had a particle accelerator, and the electronics were all at 150,000 volts, right? Well, you can't just plug that into the wall. So they had an isolation transformer that allowed you to power something and let there be a difference of 150,000 volts from here to here, okay? The physics of this is pretty simple, okay? If I set up an equation for the primary, right? My E primary, right? I'm just going to call that the voltage on the primary, is minus N, and then the rate at which the flux changes, right? Okay, so that's our D flux, right? This is Faraday's law, right? And then if I set up the EMF on the secondary, right? I'm just going to call that voltage on the secondary, right? Is minus, and this is the number of windings in the primary, right? So 1, 2, 3, 4 windings in this case, right? And then this is minus N secondary times D flux dt. Now, if this is a perfect core, if it's 100% efficient, magnetic field lines don't like escape and go outside of this secondary, okay? Some do, right? Some energy is turned into heat. That's why it's a laminated core. If that's the case, if it's 100% efficient, then we can say that these two fluxes, these two rates of flux change are the same. It's the same flux, okay? And then we end up with voltage primary over voltage secondary is N primary over N secondary, okay? And I mean, you can flip this over, but basically the voltages at the primary and secondary are proportional to the number of windings, okay? Now, as a child, I was terribly mesmerized by this. I read these How and Why Wonder books, and they showed a transformer. It was the same picture here, right? As if, you could build a transformer this way, right? Okay. And I was intrigued by this, right? I was picturing I could take a 9-volt battery. Never mind that my 9-volt battery was, AC or direct current, right? I was picturing, okay, I'm going to take a 9-volt battery, and I could do the math. I could figure out how to step this up to 120 volts, right? And so I went to my mom and I said, Mom, I've got a way. I can take this 9-volt battery. I held it in my hand. I said, Mom, I can power the city of Cedar Rapids with this 9-volt battery. And I was amazed that the adults were not smart enough to figure this out. I mean, baby, I've got it, okay? But the adults hadn't figured this out, right? And my mom said to me, she hated physics, by the way. Her father was like a PhD physicist. But she hated physics in high school, loved it in college, had a good professor, by the way. But she said to me, Chris, there's something you're missing here. There's something about you can't get something for nothing, right? My mom was remembering the first law of thermodynamics, conservation of energy, okay? So what you have to keep in mind is that the current in the primary times the voltage in the primary, that's the power delivered, yes? P is IV, right? Okay, whoops, not VV, is IV, right? Power is IV, right? So the power in the best case, is equal to the power out. Okay, that's the way it is. Don't pout about it. Okay, so I on the secondary, right? V on the secondary. This is the best case scenario, is that the power in is going to equal the power out, right? So what that ends up doing is you get an inverse thing, right? Okay, we get what I secondary, I primary. Okay, I don't use this. IB's got like a fancy thing that does this like that. You'll see it in a second here. I don't use that. I just use power in is power out. Okay, if you do that, just remember power in is power out, so that as you step the current up, as you step the voltage up, the current goes down. The power is the same. So the 9-volt battery can't power anything more than the 9-volt battery could. Okay, even if you could make it into alternating current. Okay, direct current wouldn't work. So this is, take a look at this. This is what you're going to get in the data packet, right? And I object to this. This is devoid of meaning, right? I use, instead of this thing here, I just use that power in equals power out, right? So I primary, V primary is equal to I secondary, V secondary, okay? So let's solve this problem. A transformer has 120 primary windings, so NP is 120, right? And N secondary is 1450. So this is a step-up transformer. We've got more voltage, more windings on the secondary, right? There's AC on the primary. This is voltage on the primary is 15 volts. Notice it has to be AC voltage. If it's direct current, doesn't work, right? And then our current on the primary is 350 milliamps, so 0.350 milliamps, right? Okay. All right, so let's math this thing. What is the current and voltage on the secondary? So let's figure out the voltage is going to be more, right? So let's go. I'm going to go NS over NP is VS over VP, right? So these guys are directly proportional, and you can just flip them any way you want, right? So that turns into secondary is 1450 over 120. Is equal to the voltage on the secondary divided by 15, right? So ultimately it's 15 times this fraction, right? So flip this thing anyway. I know they give it to you primary and secondary, but obviously you can flip this thing over. So 1450 divided by 120 times 15. And I get 181.25. So V secondary is 181.25 volts. All right. Is that correct? 1450, 120 primary windings. Yeah, I'm going to stand by that. 150, right? Okay, so then what is the current on the secondary? Well, power in has to equal power out, right? So the input power is IV, right? So it's 0.350 amps times 15 volts, right? This is our power in, I times V, right? Is equal to I secondary times 181.25. Okay, so 0.35 times 15 divided by the answer I just got is I secondary is equal to, in the best case scenario, 0.0289 96 amps, or 28.96 milliamps. Okay. Now another way to do that is to just use the inverse, right? So N secondary over N primary is equal to I primary over I secondary, right? So we put in 1450 over 120 is equal to, the primary is 0.35 and the secondary is, we don't know, right? Okay, so I'm going to go 0.35 times 120 divided by 1450 because of math, and I get exactly the same thing. I get that the I secondary is 0.02896 amps. Yeah. All right. So however you want to do it, but just remember that the current is such that it conserves energy. You don't get more power out of a transformer than you get into the transformer. Okay. Take a look. This is just a picture of a typical setup, right? We generate stuff at some voltage, right? They step it up. Actually, at some point, they step it up to something like 240,000 volts. And the question is, why such a high voltage? These insulators are expensive, right? Okay, you got to hold them off the ground. You got to, if trees grow up, right? That's a problem, right? So you got to cut the trees down. That also costs money, right? And so the question is, why do they use such huge voltages? And the answer is that power transmitted is I times V, right? Okay, so the bigger the voltage you transmit it at, the smaller the current, right? Power lost is I squared R, right? So the resistance of these lines, we can't do much about it, right? Okay, so the only way to reduce that power is to make that current as small as possible. And the way to do that is to transmit at tremendous voltages. Now, interestingly, natural gas has the same sort of thing going on. They transmit it from town to town or whatever, maybe from Portland to Tualatin at super high pressures. Pressure is the equivalent of voltage, right? And then they reduce that pressure outside the town somewhere, right? And then they distribute it at a certain pressure. And then even in your house, it's reduced pressure from what it is on the street, okay? So take a look at this voltage system, right? We step it up, we transmit it at a super high voltage. We'll step it down to, typically the lines going around the neighborhoods are about 10,000 volts, okay? And then outside your house, those boxes, in my neighborhood, they look like that. They're on the line like that. And they step it down to 240 or 120, right? Okay. In your neighborhood, they are little green boxes on the ground because you guys are smart enough in Tualatin to have underground utilities, right? Okay. Never mind that, if there's a windstorm, there's enough stuff above ground that you'll lose power anyway, right? So in your neighborhood, this is what they look like, right? They're little boxes in your backyard, right? In my neighborhood, they're attractive. They look like that. Okay. So these, if you look, these are the transformers. Notice that they have a little tap that goes up to, and that's the high tension line there, right? That's the one that kills squirrels. And then these lines here are as dangerous as extension cords, right? I mean, I'm not saying, go lean your ladder up against the wires going into your house. That's stupid, but, don't flip out about them either. These are the step-down transformers that are somewhere in Tualatin that are stepping it down to 10,000 volts that goes in an underground conduit to your backyard. Okay, this is what a transformer looks like in an electronic device. Notice that there's one core inside there, and that this is the primary. Here's our primary. Here's our secondary. Right, or maybe it's the other way around. I really don't know. Right, it's arbitrary. You can any transformer that has a primary and secondary, you can just use it the other way. If it's a step-up transformer, if you send the power through the other way, it'll step it down. Okay, these are just a bunch of transformers there. All right, good enough. Try these whiteboard problems.